Previously, we considered a stochastic process represented by a tennis match where Venus and Serena play tennis. There are 5 possible states. Deuce means that the 2 tennis players are tied, Venus ahead, and Venus has to win by 2. So Venus must be ahead before she can win. Similarly, for Venus to lose, she must lose by 2. So in this case, she's behind by 1, and then she has to lose again in order to lose finally. So we answered the question, given that the game is at deuce, what is the probability that Venus wins? And we had a series of equations to solve this problem. Now let's do a slightly different question, only slightly different. So in this case, we're not interested in the probability that Venus wins, but the expected time until the match finishes. That is, the expected number of points played to finish the match. For instance, if we start at deuce and Venus goes ahead and then she loses and then she wins again and then wins, that would be 1, 2, 3, 4 additional points. So that would be a time of 4. Now the time is random, so there's a probability that it will be 4 games. There's a probability that it will be more than that. It could be 1, 2, 3, 4, 5, 6. So we want to find the expected value of the number of points played. Now, let's review how we solved the previous problem of finding the probability. So this was the discussion that we had before. We wanted the probability that Venus wins given that the current state is deuce. Okay? So we write that, we represent that by little v, and this is the alternative notation that you're looking at the probability of Venus winning, which is capital V, under the assumption that you're starting at deuce. So that gives you a probability distribution that depends on D. And if the game is at deuce, there are 2 possibilities. Either the game moves to A, or where Venus is ahead, or it moves to B, where Venus is behind. You can see those 2 states here. If you're at deuce now, you either move to Venus ahead or Venus behind. So A represents Venus ahead, B represents Venus behind. And this is saying that the probability that Venus wins is the probability that Venus moves ahead, and then Venus wins starting from the state that Venus is ahead. In this case, you're looking at the probability that Venus goes behind times the probability that Venus wins given that Venus is behind. All right, so again, 2 possibilities from deuce, and you have a different probability depending on which of those 2 possibilities takes place, and you have a different probability of moving to those 2 different possibilities. So if we want to identify any of the quantities here, PD of A is the probability of moving from deuce to Venus ahead. In this diagram, that's little p. PDB is the probability of moving from deuce to Venus behind. In this diagram, that's Q. So that's why the P and the Q are replaced. Now the other question is, why is the D removed? Why is the D removed? The reason that the D is removed is that once Venus moves ahead, it doesn't matter where she came from. It only matters that she is in the ahead state. So this PD V given A actually doesn't depend on the fact that Venus came from D. It's the same as probability that Venus wins given that Venus is ahead. Similarly, this PD V given B doesn't depend on the fact that Venus moved from D. It only depends on the fact that Venus is now in state B. So we can write this equation. So this gave us an equation relating these conditional probabilities, PV given D, PV given A, PV given B, and we found 2 more equations involving those 3 quantities, and we were able to solve them. Now, what we want to do now is not deal with probabilities, but expected times. But expectation works exactly the same way. If you replace this P, if you replace these P's with E's, then the same or a similar construction takes place. So that's what I'm going to do down here. All right, so instead of doing little v, which is the probability that Venus wins, eventually wins, given D, I'm going to do little n, which is the expectation of the additional points played, given that the game now is in deuce. And the additional points played, that will be my random variable that I'll call capital N. Again, that's random because it could be 4, it could be 6, and so on. So again, instead of writing this notation E n given D, I write that ED of n, which means I'm looking at the distribution starting at deuce, and I want the number of additional points played. So what we have, let me zoom out a little bit so we get everything in. Okay. So if we want to get this expectation, we can write it in terms of conditional expectations. Just as before, there are two possibilities of moving from D. You can move to A or you can move to B. So I'm breaking up my expectation in terms of those two possibilities. All right? So here I have the contribution in case Venus moves to A, and here I have I'm sorry, not just Venus, but the tennis game moves to A. And here I have the possibility in case the tennis game moves to D. Now, instead of just having expectation, I have expectation plus 1. Why is that? Because if the game moves to A, that's 1 point played. So we've added 1 to the number of points played. Then this would be the number of additional points played after the game reaches A. So we have to take one game to reach A, and then we have a number of additional points played, and that will be the total number of points played until the game is finished. Here we still have PDA as before. Similarly, we have this contribution from B. We're moving to B with probability B, to probability PD of B, and the number of points played is then 1, because you take 1 point to move to B, and then you have these additional points played. Right, now, just as before, we can replace this PDA with P and this PDB with Q. Of course, P equals 1 minus Q in this case, but it's shorter to write the equations this way. So if I make that replacement, then I have this. Now I really, just as before, I don't need the D here. I can remove the D because this expectation only depends on the fact that I'm at A. And this expectation only depends on the fact that I'm at B. So I can say this is independent of D, and this is independent of D. So I don't need to include those. All right. Now, the nice thing is that this P plus this Q combines together to give 1. So that simplifies the equation. So we get an equation relating the ED of n, and then this E of n given A, which is the same as EA of n, and this is EB of n. So why don't I just write down the equation finally that we get. So the final equation for this case is that ED of n is equal to, this I can write as EA of n times P. This one I can write as EB of n times Q. And then this P plus Q together combines to 1. Okay. So that's one equation, and we need 2 more equations for these 3 quantities. ED of n, EA of n, and EB of n. And once we have 3 equations, we have 3 unknowns, 3 equations, and we can solve the problem. Okay, so it's as simple as that.